Dear students, welcome to this Friday lectures. And in this lecture, we will continue with sections 441 and 442. And in the present lecture, it will be section 441, and the lecture to follow will be 442. But before we do that, we will recap what we have done last time. And we have defined in sections 4.1 and 4.3 the notion of stochastic integral, also called the Ito integral with respect to Brownian motion, and we have derived its properties. We will repeat this derivation very fast, and after that we will learn this Ito-Doeblin formula, which in fact is a special rule, like the rules that we have learned before for regular integration, like integration by parts, for example. We will do that now for the stochastic integral, and then it's called the Ito-Doeblin formula. But again, first a short recap. Remember that we started with simple processes. We defined first the Ito integral for simple processes. And the basis was then we are given a Brownian motion, Wt, t greater or equal to 0, and it's defined on a probability space omega fp with its filtration ft t greater or equal to 0. And then we know a lot of properties of our Brownian motion, as we mentioned. It's adapted to the filtration. And these are important informations and knowledges. Now, the starting point in 4.1 was the simple process. And the simple process is an adapted process with respect to that filtration. We wrote it down as delta t, t running from 0 to capital T, a bounded time interval, the time interval which can be the interval for a financial contract, which terminates at capital T, for example. It is adapted to the filtration of the Brownian motion. And if we are dealing with a simple function, then there is a partition of that time interval 0t, where t0 is equal to 0, it's less than t1 up to tn, and tn is then equal to t. So this is our time partition, the basis of the simple process, and then delta is written in this case as a sum. I is running from 0 to n minus 1, delta ti, where this ti is the left side point of the interval times the indicator function of the interval ti to ti plus 1. So this is a piecewise constant function. It has value delta ti on that interval, and that particular sum is 0 elsewhere, and for another interval it has another value delta ti, and again that is then constant over the small interval. So in the case of a simple process, delta t is a constant on each particular interval, ti plus 1, and it has the value of the left side, delta ti. Now, for the simple process, we can define the Ito integral, or the stochastic integral. And that was done as follows. The Ito integral of a simple process, delta t, t between 0 and capital T, is defined as follows. The basis is that we assume, or we pick an interval from tk to tk plus 1 where our t lies in. So we say small t is in that interval from tk to tk plus 1. Then our Ito integral for the simple process is defined as follows. We write it as it. It is, in fact, the integral from 0 to t, delta u dwu. So an integral with respect to Brownian motion. And we define it as the sum, I runs from 0 to k minus 1, of delta ti times the Wiener increment, the Brownian increment WTI plus 1 minus WTI. This is for all the elements up to tk. So delta tk minus 1, wtk minus wtk minus 1 is the last of these intervals. And in the very last one, that is the interval in which t lies, is written as delta tk times wt minus wtk. So all these terms are added, and that is the definition of the integral of a simple process. Well, we have also seen, and we have proved all the properties of such an Ito integral. And remember the properties, they are important. We will use them often, so try to remember them. First of all, t between 0 and capital T has continuous paths. Secondly, it is a martingale. Third, we have seen that, of course, I0 is equal to 0. And because of that, and because of the martingale property, we can say that the expected value of it, that is nothing but the expected value of I0, and that is equal to 0. So it has 0 expectation. And because of that, we also can say something about the variance of it. It is, in fact, the expected value of I squared. And if we write that down, that is the expected value of this integral from 0 to t, delta u dwu square. And here we can use that formula, the Ito isometry, which basically means that we can move the square inside the integral, and it gives us that this is in fact equal to the expected value of the integral from 0 to t of delta square du. And finally, related, the quadratic variation of I in square bracket I of t is the integral from 0 to t of delta square u du. These were the properties that we were heavily using and that we have proven for simple processes. Then in the next step, we moved from the simple processes towards the more general adapted processes. So in that case, we didn't prove things, but we outlined the proof. It can be proved with the help of measure theory. We gave you the outline for the integral for general processes. It went as follows. Now, if delta t, small t running from 0 to capital T, is a general adapted process, and it satisfies this technical condition, the technical condition that the expectation of this integral from 0 to t of delta square t dt is finite. And let's look back, you see that this is connected to this here or to this here. So it's connected to, and because it's connected to this one, it's also connected to this one. So it says finite variance for this integral. Then we approximate delta by simple processes, call them delta sub n t, t running from 0 to capital T, and delta sub n is defined as follows. So delta n t is the integral from 0 to t delta nu dwu. And with this, we can prove convergence. Convergence can be proved. Convergence of in, of these ins, convergence of these ins in L2 for n to infinity, convergence towards the Ito integral for the general process. The Ito integral for the general process, the integral from 0 to t, delta u dwu. So with the help of the simple processes, we can prove convergence in L2 for n to infinity. Recall convergence in L2. the distance between delta n and delta squared, the integral from 0 to t du, and the expectation of that goes to 0 when n goes to infinity for convergence in L2. And essentially that basically means that the expectation of the integral from 0 to t of delta nu minus delta u dwu squared converges. And this also inherited the properties of the Ito integral for the simple processes. That was important. The properties that we have just listed and that we will list again, the properties of the Ito integral for the simple processes, they generalize towards these more, the integral for these more general processes. And these properties, again, recall the first one, IT, in the case of general adapted processes, has continuous paths. It is adapted to the filtration of Brownian motion. It is linear. We have the martingale property, so it is a martingale. Fifth, it satisfies the Ito isometry as follows. So written as follows: the expected value of this integral squared is in fact the expected value of this integral from 0 to t delta squared du. And connected the quadratic variation. The sixth property, quadratic variation of I, is the integral from 0 to t delta square u du. So that was the short recap, the things that we know from last lecture. And now we will work with it. So we will come with these special integration rules in order to simplify our work when we need to integrate with respect to Brownian motion. So we want to work with integration, and we would like to have rules for integration in the case of a stochastic integral. So given a Brownian motion, Wt, t running from 0 to capital T, and a filtration, f script ft, t between 0 and capital T again. And now suppose we have a continuously differentiable function, fx, a function of one variable only, x. It goes from r to r, and the second derivative is continuous. Now in this case, the Ito-Doeblin formula tells us that f with argument wt minus f with argument w0 is equal to the integral from 0 to t of f prime wu dwu plus 1/2 the integral from 0 to t f double prime wu du. So this is the Ito-Doeblin formula in the case of one variable only, the x variable. Later, in the next slide, we will deal with functions of time and space, so f of t and x. But for now, we look at functions that only depend on x. And what we see here we see something like a chain. Yeah, f prime w dw. And we have an extra term here because of the stochastic integral, and that is something like a quadratic variation, a double prime term times du. So we have the chain rule term, the first one, and we have an extra term due to the quadratic variation. And in differential form, if we look at this in differential form, then this difference, we can write it as dfwt, the change in fwt, and it is connected to f prime wt dw plus 1/2 f double prime wt dt. And this reminds us a little bit of, indeed, of a chain rule type expression with a special expression here. And at the same time, it also reminds us a little bit of a Taylor formula, the Taylor expansion. But the formula, as mentioned, is more general. So it applies not only to functions that only relate to x, but it also relates to functions that depend on t and x, satisfying certain differentiability conditions. Derivatives should exist, and we will pose the Ito-Doeblin formula as a theorem in the next slide in the more general form. Okay, now we have our theorem, the Ito-Doeblin formula for Brownian motion. And the basis for this is a function f which depends on t and x. So let f of t and x be a function so that the first derivative with respect to time, the first derivative with respect to space, and the second derivative with respect to space, they all exist and are continuous. So we use the subscript notation. F sub t stands for df dt. F sub x stands for df dx. And f subscript double x stands for the second derivative of f with respect to x. They should all exist. And furthermore, let wt, t greater or equal to 0, be a Brownian motion. Then Ito-Doeblin's formula for the Brownian motion tells us the following. For all t greater or equal to 0, we have that f, depending on capital T and W capital T, is equal to f0 w0 plus the integral from 0 to capital T. The first derivative of f with respect to t with arguments t and wt dt, plus the integral from 0 to capital T fx dw, plus 1/2 the integral from 0 to t fxx dt. This is in fact Ito-Doeblin's formula for Brownian motion. So we see a derivative with respect to time times dt, a regular integral, an integral with respect to w, so a stochastic integral fx dw, plus the extra term 1/2 the integral from 0 to t, the second derivative of f with respect to x times dt. So how does this come about? Well, how do we prove that? Well, it can all be done in a rigorous way, but we will only sketch a proof. And the basis for this proof is the two-dimensional Ito formula. So let's look at it. As a sketch, we fix capital T final time greater than 0, and we consider a partition as follows. Again, T0 is equal to 0, it's less than T1, less than T2, less than T3, up to Tn, which is equal to T. That is a partition from 0 to T. Then, if we look at this difference, Ft Wt, capital T, it is minus F0 W0, we can rewrite that as a telescopic sum. And this is a sum, I runs from 0 to n minus 1, F Ti plus 1 W Ti plus 1 minus F Ti W Ti. And you see that what you add in one of the indices, you subtract again in the other. So in fact, this is indeed an identity. These are indeed the same. But now with this right-hand side, we can apply the Taylor expansion. So we are in a little time instance, a little difference from Ti plus 1 to Ti and Wti plus 1 Wti. So what we can do now is we can apply the Taylor formula to each term. To each term in the right-hand side, it is. And the first one, f at Ti plus 1 Wti plus 1 minus Fti Wti. The first one is, of course, the derivative with respect to t. So this is the sum, I runs from 0 to n minus 1, of the first derivative of f with respect to t at the point Ti Wti times the time increment Ti plus 1 minus Ti. That's the first part. Second part, that is, of course, the second argument here. And that gives us a sum. I runs from 0 to n minus 1 of the first derivative of f with respect to x at the point ti wti times the increment in the second argument w ti plus 1 minus wti. And the third term here is the following. So think of Taylor, 1/2 sum I runs from 0 to n minus 1, the second derivative of f with respect to x at the point ti wti times the distance in the second argument square, wti plus 1 minus wti square. And these terms we recognize, of course. We have worked with these Brownian increments square before. Now we have another term. Of course, we have a second derivative with respect to time. 1/2 again from the Taylor expansion, 1/2 the sum, second derivative of f with respect to time at the point ti wti times ti plus 1 minus ti square. And we have the mixed term, and we have two mixed terms, ftx and fxt. And if we combine them, if we add them together, we get rid of our 1/2. So we end up with the sum I runs from 0 to n minus 1, the mixed term, the mixed derivative df dx dt at the point ti wti times the increment in time, ti plus 1 minus ti times the increment in the Brownian motion, wti plus 1 minus wti. Plus, of course, we can do the Taylor formula further and further, so we get higher order terms, HOT, higher order terms, that converge to 0 when n goes to infinity. Now let's look at all of these terms separately. So the first term is this one, we call it I1. The second one, we call it I2. The third one, we call it I3. The fourth one, we call it I4. And the fifth one, we call it I5. And now let's take the limit n to infinity, the time interval, the intervals going to 0, the number of points going to infinity, and let's see where these terms will end up. And that's on the next slide. I1, when n goes to infinity, I1, recall that is this one, so a regular one, a Riemann sum, if you wish, df dt times this increment, and that indeed converges to the integral from 0 to t ft dt. The second one, this one, the sum of df dx times this Brownian increment. In fact, when n goes to infinity, that also will go to the integral from 0 to t fx t wt. There is always a bracket missing here, I see, times dwt. The third one is in fact this one, and here we recognize this Brownian increment squared, and for delta t going to 0 and the number of points going to infinity, we know that this will converge to dt, in fact, right? Second derivative of f with respect to x times dt. And indeed, that's the case, right? With dwt being equal to dt, the third term for n to infinity will converge to 1/2 the integral from 0 to t, the second derivative of f with respect to x times dt. The fourth term is this mixed term. Well, this mixed term of, no, this is a dt square term, and we have also seen when we did the cross variation and also the second, so the dt square term, we have argued in a previous lecture that this will indeed converge to 0. And that is indeed the case. The fourth one will converge to 0. I do not write it out here, but I have it on a slide. So you will see the slide. Essentially, this is in the same, with the same argumentation as we did when we looked at the cross variation. And the fifth one, recall that the fifth one looks like this. It's a mixed term with a dw dt term. And we have also given arguments in a previous lecture that this will also converge to 0 when n goes to infinity. When the partition, it was all based on the partition, when the partition went to, in the number of points in our partition went to infinity, and the size of the partition, the maximum size in the intervals went to 0, then this would converge to 0. And again, the argumentation is written down. So the proofs of the letter 2 are similar to those we used to show that the cross variables and the quadratic variation of t is equal to 0. And it is in fact exactly the same that we're using here. I have it on the slides, so it will be in the lecture notes on the slides that are posted. This is I4 and I5. So let's recap. What did we find? What is the Ito-Doeblin formula for Brownian motion? In fact, it says that if we have a function of time and of Brownian motion, a function of t and of w, then this function is equal to f at 0, w0, plus the integral from 0 to t fu du, plus the integral from 0 to t fx dw, plus 1/2 the second derivative of f with respect to x times du. And particularly this part is a new part. So this is the Ito-Doeblin formula for functions that depend on t and on Brownian motion, and on another function, a stochastic function. And in differential form, we can write it as follows. So these two, if this one goes to the left-hand side, we see df of t and w. That is then equal in differential form to the integrand over here, ft dt plus fx dw plus 1/2 the second derivative of f times dt. And this is a form that we will often work with. And the examples that we have seen before, we can now do with the help of this integration rule and differentiation rule. So this is a rule that we can use, a rule that we can use. It says if we have a function, we should look at its first derivative in time, its first derivative in space, its second derivative in space, and with the help of these derivatives, we can find an expression for the function. All right. Let's do an example. And let's do the example, actually the example that we did in the previous lecture. We have proved before, by means of the definition of the stochastic integral, we have proven that the integral from 0 to capital T of wt dwt is in fact 1/2 wt squared minus 1/2 t. Now we can derive this formula again in a very convenient way, hopefully using the Ito-Doeblin formula. And that goes as follows. We should look for a function f, and with this function f, we should look at its derivatives, and by this we should be able to find this expression. Now, the first idea is let's use fx is 1/2 x squared. So this is a function that doesn't explicitly depend on t. So it is a function that depends on one argument here. We call it x. So let's look at 1/2 x squared and see how far we get with the Ito-Doeblin formula. Well, if we have this, of course, the first derivative with respect to time is equal to 0. We don't have it. And we only need to look at the first and second derivatives with respect to x. And that is, of course, the first derivative is x and the second derivative is equal to 1. Now, plugging this all in the Ito-Doeblin formula gives us the following. So f of with argument wt is by definition now the function f was 1/2 x squared, so it's 1/2 wt squared. And we know that is equal to the function at 0. Well, the function at 0, w 1/2 w squared at 0, that will be 0, right? And then we have the integral from 0 to capital T of the first derivative dw plus 1/2 the integral from 0 to capital T of the second derivative dt. Plugging in all the terms, first one again was 0 as mentioned. The second one, the first derivative of the function was the function itself, right? Fx, so we had 1/2 x squared. And the first derivative is x, and for x we substitute wt, so we get the integral from 0 to capital T, wt dwt. That is the result of this first expression. And the second one was a constant, 1. So we end up with 1/2 the integral from 0 to t times dt, with a 1 in front. It's just dt. So if we finally consider this we just copy. It's the integral from 0 to capital T, wt dwt plus 1/2 times t. Now connecting the left and right hand side, this is the left hand side, this is the right hand side, and you see that this goes in the good direction for the approximation of this integral. This integral is in fact then 1/2 wt squared minus 1/2 times capital T. And that was exactly the expression that we also found in the last lecture on the basis of the definition of the stochastic integral. So the integral from 0 to t, wt dwt is 1/2 wt squared minus 1/2 t. So you see these integration rules are convenient and easily applied, and you can use them for many different functions and expressions, right? And let's do another example. So let's use Ito-Doeblin's formula in order to prove that the expected value of a Brownian motion cubed is equal to 0. So we look at the expectation of w cubed at time point capital T, and that should be equal to 0 for any t greater or equal to 0. And we will encounter in this derivation the integrals of the form the integral from 0 to t, w squared t dwt. Now, in order to use Ito-Doeblin, let's again choose a function for which we will apply this formula. And the function that we will be choosing here is x cubed over 3. Yeah, so our f with argument x is x cubed over 3. It is a continuously differentiable function. It doesn't depend on t, only on x. So we only need the first derivative with respect to x and the second derivative with respect to x. And they are easily found, of course. The first derivative for such a function, as you know, it's x squared. And the second derivative is then 2 times x. Well, with this information already, we can apply the Ito-Doeblin formula to this expression, and then later we substitute for x wt, of course, right? That's how we do it. So applying Ito-Doeblin's formula, a function of wt, in this case is w cubed at final time capital T over 3. So indeed, we replace x by wt. And then Ito-Doeblin's formula tells us this is equal to w cubed at 0/3 plus the integral from 0 to t of x squared, so w squared dwt plus 1/2 double the second derivative 2x, so plus 1/2 the integral from 0 to capital T 2 times wt dt. And again, we can substitute all the terms that we know. So we know particularly this one is equal to 0. So this one cancels out. And then we should take the expectation, right? We look for an expected value of this. So we should take an expectation. So we had w cubed over 3. We multiply left and right hand side by a factor of 3. So the first term cancels out, as we mentioned. So w cubed at final time capital T is equal to 3 times the integral from 0 to capital T, w squared dwt, plus 3 times the integral from 0 to capital T, wt dt. This is the expression that we have, and now we should take expectations. And let's notice here that this, in fact, this is an Ito integral, right? Here we have the Brownian increment, so dw, so our delta in this case is w squared. So we have here an Ito integral, and we know things for the Ito integral. For example, we know the expected value of the Ito integral being equal to 0, for example. So we can benefit from that. We take expectations, and then, as mentioned, we use the fact that this integral over here is an Ito integral. Taking expectations, left and right hand side, expected value of w cubed, the one that we are aiming at, is 3 times the expectation of the Ito integral from 0 to t, w squared dw, plus 3 times the expected value of the integral from 0 to capital T, wt dt. And now this is equal to 0. First of all, this term here, it has expectation 0. That is known because it's an Ito integral. And the other term is a little bit more tricky. But we are dealing with a bounded function here. And in fact, we are dealing with 2 integrals, because the expectation is an integral. And then inside the expectation, we are also dealing with an integral from 0 to t. And now we can use Fubini's theorem to actually interchange the expectation with the integral. So we can interchange these, giving rise to 3 times the integral from 0 to t, the expected value of wt dt. And there we recognize the expectation of a Brownian motion, and that is equal to 0. So also therefore this term will be equal to 0, and in total we find that the expected value of w cubed is equal to 0. So that is another example of the convenience of the Ito-Doeblin formula in order to work with stochastic integrals. I thank you for your attention for this first lecture.